Ascending item price auctions. Figure 11.3 describes an auction that is very natural from an economic point of view. Increase price gradually, maintaining a tentative allocation until no item that is tentatively held by one bidder is demanded by another. Intuitively, at this point, demand equals supply, and we are close to a Voration equilibrium discussed earlier in section 11.3, which, by the first welfare theorem, is socially efficient. Of course, we know that a Voration equilibrium does not always exist in a combinatorial auction. So this cannot always be true. The problem is that the auction does not ensure that items are not under-demanded. It may happen that an item that was previously demanded by a bidder is no longer so. The following class of valuations are those in which this cannot happen. Definition 11.28. The valuation VI satisfies the substitutes or gross substitutes property if for every pair of item price vectors Q arrow, which is greater than or equals to P arrow, is coordinate-wise comparison. We have that the demand at prices Q contains all items in the demand at prices P whose price remained constant. Formally, for every A, which is in the argument max of the set V of S minus the summations of Pj, summing for all j in S, where the maxima is taken among all possible S, there exists D in the argument max of the set V of S minus the summations of Qj, summing for all j in S, and the maxima is taken among all possible S again, such that D is a superset or equals to the set that J is in A, such that Pj is equals to Qj. That is, the only item that could drop from the demand when prices change from P arrow to Q arrow are those whose price has strictly increased. The substitutes property rules out any form of complementarities. For example, a single-minded bidder who is willing to pay $10 for the complete bundle, the set AB, will demand both items at prices 3, but if the price of B is raised to 8, this bidder will no longer demand any item. Contrarily to the requirement of a substitute valuation, exercise 11.6 shows that, in general, substitute valuations must be submodular. It is not difficult to see that this class of valuations contains the classes of additive valuations, unit demand valuations, and downward sloping valuations. See definitions 11.17 and 11.19. With such valuations, the auction maintains the property that every item is demanded by some bidder. The auction terminates when all the bidders receive their demanded bundles, and consequently, the auction converges to a nearly Voration equilibrium. Definition 11.29. An allocation S1, S2, S3 until Sn, and the prices P1, P2, P3 until Pn, or an epsilon Voration equilibrium, if the union of the set Si, union among all possible index I, is a superset or equals to the set J such that Pj is greater than 0, and for each I, Si is a demand of I at prices Pj for j in Si, and Pj plus epsilon for all j not in Si. Theorem 11.30. For bidders with the substitutes valuations, the auction described in figure 11.3 ends with an epsilon Voration equilibrium. In particular, the allocation achieves welfare that is within an epsilon from the optimal social welfare. Proof: the theorem will follow from the following key claim. Claim 11.31. At every stage of the auction, for every bidder I, Si is a subset equals to Di. First, notice that this claim is certainly true at the beginning. Now let us see what an update step for some bidder I causes. For I itself, Si after the step is exactly equal to Di, note that the changes in prices of items just added to Si exactly matches those defining Di. For k not equals to I, two changes may occur at this step. First, items may have been taken from Sk by I, and second, the prices of items outside of Sk may have increased. The first type of change makes Sk smaller while not affecting Dk. The second type of change does not affect Sk, and the substitute property directly implies that the only items that can be removed from Dk are those whose price strictly increased and are thus not in Sk. Once we have this claim, it is directly clear that no item that was ever demanded by any player is ever left unallocated, i.e. the union of Si, union among all possible index I, always contains all items whose price is strictly positive. Since the auction terminates only when all Di equals to Si, we get an epsilon Walrasian equilibrium. The fact that an epsilon Walrasian equilibrium is close to socially optimal is obtained just as in the proof of the first welfare theorem, theorem 11.13. Since prices are only going up, the algorithm terminates after at most m times Vmax over epsilon stages, where Vmax is the maximum valuation. It may also be useful to view this auction as implementing a primordial algorithm. The auction starts with a feasible solution to the dual linear program, here zero prices, and as long as the complementary slackness conditions are unsatisfied, proceeds by improving the solution of the dual program, i.e. increasing some prices. Finally, we will address the strategic behavior of the bidders in such ascending auctions. Will strategic bidders act myopically and truthfully reveal their demand in these auctions? If the valuation functions have complementarities, then bidders will clearly have strong incentives not to report their true preferences due to a problem known as the exposure problem. Bidders who bid for a complementary bundle, e.g. a pair of shoes, are exposed to the risk that part of the bundle, the left shoe, may be taken from them later, and they are left liable for the price of the rest of the bundle, the right shoe, that is worthless for them. However, even for substitutes preferences, the incentive issues are not solved. The prices in a Walrasian equilibria are not necessarily VCG prices, and therefore truthful bidding is not an exposed equilibrium. The strategic weakness of a Walrasian equilibria is that bidders may have the incentive to demand smaller bundles of items, demand reduction, in order to lower their payments. The following example illustrates such a scenario. Example 11.32. Consider two items A and B and two players, Alice and Bob, with the following substitutes valuations. VAVV and V of AV for Alice is 444. V of A, V of B, V of AB for Bob is 5510. For these valuations, the auction in figure 11.3 will terminate at the Walrasian equilibrium prices PA equals to 4, PB equals to 4, where Bob receives both items and earning him a payoff of 2. If Bob placed bids only on A during the auction, then the auction would stop at 0 prices. Allocating A to Bob and B to Alice, with this demand reduction, Bob improves his payoff to 5.